A central processing unit, CPU, often referred to as a central processor or just processor, serves as the primary processor in a computer system. Its electronic circuitry carries out the instructions of a computer program, encompassing tasks like arithmetic, logic, controlling, and input-output I/O operations. This pivotal function stands in contrast to external elements like main memory and I/O circuitry, along with specialized coprocessors like graphics processing units, GPUs. Despite changes in their form, design, and implementation over time, the core operation of CPUs has remained largely consistent. Key components of a CPU include the arithmetic logic unit, ALU, for performing arithmetic and logic operations, processor registers for providing data to the ALU and storing operation results, and a control unit responsible for coordinating the fetching, decoding, and execution of instructions by managing the synchronized actions of the ALU, registers, and other elements. In modern times, CPUs allocate a significant portion of semiconductor space to caches and instruction-level parallelism to enhance performance, along with offering CPU modes to support operating systems and virtualization. Most present-day CPUs are built on integrated circuit IC microprocessors, containing one or more CPUs on a single IC chip. Microprocessor chips featuring multiple CPUs are termed as multi-core processors. These individual physical CPUs, known as processor cores, may also incorporate multithreading to enable CPU-level multithreading. An IC housing a CPU might also integrate memory, peripheral interfaces, and other computer components. These complex integrated devices are referred to as microcontrollers or systems on a chip, SoC. During the early days of computing, machines like the ENIAC required physical rewiring for different tasks, earning them the moniker fixed-program computers. The concept of the central processing unit was coined around 1955, and the advent of stored program computers marked the birth of CPUs. Although the ENIAC initially lacked a stored program design, the notion was present in its blueprint envisioned by John Presper Eckert and John William Mauchly. A pivotal moment came on June 30, 1945, when mathematician John von Neumann introduced a paper outlining the stored program computer concept in the EDVAC, finalized in August 1949. Unlike the ENIAC, the EDVAC stored instructions in high-speed memory, enabling easier program modifications. Other early stored program computers like the Manchester Baby and Manchester Mark I preceded the EDVAC's operational programs in 1948 and 1949, respectively. Initially, CPUs were custom-made for specific applications, but this practice transitioned to the mass production of multi-purpose processors with the rise of integrated circuits, ICs. The standardization of CPUs commenced during the transistor era and progressed swiftly with IC popularization, leading to nanometer-level manufacturing tolerances. The miniaturization and standardization of CPUs expanded their presence from specialized machines to ubiquitous digital devices in modern times. Notable contributors to the stored program computer concept include John von Neumann and Konrad Zuse, with the Harvard architecture also playing a role in early designs utilizing punched paper tape for program storage. The shift to transistor-based CPUs in the 1950s and 1960s eliminated the need for bulky and unreliable components like vacuum tubes and relays, paving the way for more complex and reliable systems housed in printed circuit boards. IBM's introduction of the System 360 architecture in 1964 brought compatibility across a series of computers, revolutionizing the industry by incorporating the concept of microprograms or microcode. Among the successful computers of that era was DEC's PDP-8, aimed at scientific and research applications. Transistorized CPUs offered enhanced reliability, lower power consumption, and increased operating speeds, facilitating clock rates in the tens of megahertz range. Moreover, the era saw the emergence of high-performance designs like SIMD vector processors, laying the groundwork for specialized supercomputers produced by companies such as Cray Inc. and Fujitsu Ltd. The development of integrated circuits, ICs, enabled the miniaturization of digital circuits, giving rise to small-scale integration, SSI, CPUs. Apollo Guidance Computer and IBM's System 370 utilized these SSI ICs to enhance performance while reducing space and power requirements. The advancement into large-scale integration, LSI, further consolidated transistors on a single chip, with notable figures like Lee Boyce advocating for building mainframe computers from a small number of LSI circuits. The transition from bipolar transistor logic to MOS ICs in the late 1970s significantly improved chip technology, gradually increasing transistor density on ICs and decreasing the number of components necessary for a complete CPU. By 1968, the PDP-11 marked a breakthrough with a CPU composed of only 4 LSI integrated circuits, a remarkable contrast to earlier implementations. Microprocessors have become the predominant form of central processing unit since their inception. The Intel 4004, developed in 1971, marked the advent of commercially available microprocessors integrating arithmetic logic unit, control unit, and register unit on a single chip. Subsequently, the Intel 8080 in 1974 became widely utilized, leading mainframe and mini-computer manufacturers to create instruction set compatible microprocessors. This backward compatibility allowed for easy integration with existing hardware and software. The proliferation of personal computers solidified the association of the term CPU with microprocessors. In contrast to previous CPU generations consisting of multiple discrete components on circuit boards, microprocessors are manufactured on a small number of integrated circuits, often just one. This condensed design results in faster switching times and higher clock rates due to decreased gate parasitic capacitance. Microprocessors have undergone significant advancements in size reduction and transistor complexity since the 1950s. Despite these changes, the fundamental design and function of CPUs have remained relatively stable over time. Most modern CPUs adhere to the von Neumann stored program machine architecture. However, the apparent end of Moore's law has prompted concerns regarding the limits of integrated circuit transistor technology. Factors such as extreme miniaturization, leading to issues like electromigration and subthreshold leakage, have spurred exploration into quantum computing and increased utilization of parallelism to enhance traditional von Neumann models. In terms of operation, CPUs execute stored instructions as part of a program. The instruction cycle involves fetching, decoding, and executing instructions stored in computer memory. Following the execution of an instruction, the cycle repeats with the program counter incrementing to fetch the next instruction in sequence. More complex CPUs can process multiple instructions simultaneously, as seen in the classic RISC pipeline found in many electronic devices. Instructions can alter the program counter or modify flags in a register to influence program behavior. The fetch stage involves retrieving instructions from program memory using the program counter. In the decode stage, the instruction is translated into signals that control other CPU components based on the instruction set architecture. The execution step can encompass a single action or a series of actions where control signals activate specific parts of the CPU to perform the required operation in response to a clock pulse. Results are typically stored in internal CPU registers or main memory for subsequent instructions. In a CPU's circuitry, there exists a predefined set of fundamental operations known as an instruction set. These operations could involve tasks such as adding or subtracting numbers, comparing values, or altering the program flow. Each operation is encoded by a distinctive bit pattern referred to as the machine language opcode. During the execution of an instruction, the CPU decodes the opcode using a binary decoder to generate control signals that govern the CPU's actions. A machine language instruction comprises the opcode and, in many cases, extra bits specifying operation arguments, like the numbers to be computed in an addition. The actual computational tasks for each instruction are carried out by a combinational logic circuit inside the CPU called the arithmetic logic unit, ALU. The CPU typically executes an instruction by fetching it from memory, using the ALU to process it, and then storing the outcome back to memory. Apart from instructions for integer arithmetic and logic, there are other machine instructions for loading and storing data, branching, and handling floating point arithmetic through the CPU's floating point unit, FPU. The control unit, CU, is a vital component of the CPU that manages and coordinates the processor's operations. It instructs the computer's memory, arithmetic, and logic unit, and input-output devices on how to respond to received instructions. By providing timing and control signals, the CU regulates the functions of the other units within the CPU, handling data flow between the CPU and external devices. The arithmetic logic unit, ALU, is a digital circuit responsible for performing integer arithmetic and logical operations within the processor. The ALU receives operands, data words to operate on, status information from previous operations, and operation codes from the control unit to determine the required computation. Following the processing of input signals through the ALU circuitry, the result of the operation emerges at the ALU's outputs, containing a data word and status details stored in a special CPU register. Within the CPU, the Address Generation Unit, AGU, or Address Computation Unit, ACU, is an execution unit dedicated to calculating memory addresses essential for accessing main memory during CPU operations. By offloading address calculations to specialized circuitry operating in parallel with the CPU, the AGU reduces the number of CPU cycles needed for executing instructions, consequently enhancing performance. CPUs rely on address generation calculations for tasks such as fetching data from memory, requiring operations like addition, subtraction, modulo, or bit shifts. Incorporating an AGU into CPU architecture and introducing specialized instructions utilizing the AGU optimize address generation tasks, potentially performing them in a single CPU cycle. The capabilities of an AGU vary based on CPU designs, with some offering more address calculation operations and advanced instructions for multitasking. In the realm of memory management, many microprocessors feature a memory management unit, MMU, responsible for translating logical addresses into physical RAM addresses, providing memory protection and enabling virtual memory functionalities. Advanced microprocessors incorporate CPU caches, which are smaller, faster memories located close to the processor core. These caches store frequently accessed data from main memory, reducing the time and energy required to retrieve information. CPUs typically include instruction and data caches organized into multiple levels, L1, L2, L3, etc., with varying sizes and speeds. Each cache level serves different purposes, with L1 cache being the fastest and closest to the CPU, and modern CPUs integrating multiple cache levels to improve performance. Synchronous CPUs utilize a clock signal to coordinate their sequential operations, with the clock frequency determining the execution rate of instructions. To ensure proper CPU functionality, the clock period is set above the maximum signal propagation time within the processor, simplifying CPU design and component count. However, synchronous CPUs may face challenges with rising clock rates, such as maintaining signal synchronization and managing increased energy consumption and heat dissipation. Techniques like clock gating are employed to control energy consumption by deactivating unused components. Notably, some CPU designs, like the IBM PowerPC-based Xenon in the Xbox 360, implement extensive clock gating to reduce power requirements. Removing the global clock signal is a method to address issues in CPU design, leading to the development of asynchronous designs, which offer advantages in power consumption and heat dissipation. Notable examples include the Amulet and Mini-MIPS CPUs, which operate without a global clock signal. Moreover, some CPU designs utilize asynchronous components like ALUs alongside superscalar pipelining to enhance arithmetic performance. While the performance of asynchronous designs compared to synchronous ones is debatable, it is evident that they excel in simpler math operations. These CPUs are particularly suitable for embedded computers due to their low power consumption and heat dissipation capabilities. Additionally, modern CPUs incorporate a die-integrated power managing module to regulate voltage supply based on demand, balancing performance and power usage effectively. In terms of numerical representation, most modern CPUs use binary representation with word sizes that are powers of 2, such as 8, 16, 32, or 64 bits. The size and precision of integer numbers that a CPU can represent are determined by its word size, affecting the range of integer values it can directly process. Larger word sizes allow for greater data ranges and address spaces, but come with increased complexity, cost, and power consumption. To mitigate this, some CPUs feature internal data paths shorter than the word size. Furthermore, CPUs often implement varying bit widths for integer and floating point data to optimize performance. Parallelism plays a crucial role in CPU design, with the subscalar CPUs operating on one instruction at a time, resulting in inherent inefficiency. Additional execution units may not significantly enhance performance, as they can lead to increased idle transistors when instructions take more than one clock cycle to complete. To overcome this, CPUs have implemented design methodologies focusing on increasing instruction-level parallelism, ILP, and task-level parallelism, TLP. ILP targets executing instructions more rapidly within a CPU, while TLP aims to execute more threads or processes simultaneously, each offering unique benefits in enhancing CPU performance for various applications. Instruction pipelining is a technique used in most modern general-purpose CPUs to enhance parallelism by initiating the fetching and decoding of new instructions before the current instruction completes its execution. This method breaks down the execution pathway into stages, allowing multiple instructions to be processed concurrently, similar to how an assembly line operates. However, pipelining can encounter data dependency conflicts when the result of a previous operation is required to complete a subsequent one. To address this issue, pipelined processors must identify and manage these conflicts to prevent delays. Superscalar pipelines go a step further by fetching and dispatching two instructions simultaneously, enabling the completion of up to 2 instructions per clock cycle. These designs with improved instruction pipelining have significantly reduced the idle time of CPU components. Superscalar architectures incorporate multiple identical execution units, such as load store units, arithmetic logic units, and floating point units, enhancing their ability to execute instructions in parallel. The dispatcher in a superscalar pipeline determines if instructions can be executed concurrently and dispatches them to the appropriate execution units for simultaneous processing. Effective dispatcher design is crucial in maximizing CPU performance by keeping execution units busy and ensuring the instruction pipeline is consistently filled. Modern processors utilize hazard-avoiding techniques like branch prediction, speculative execution, register renaming, and out-of-order execution to maintain high levels of performance. By predicting the outcome of conditional instructions, CPUs can minimize pipeline stalls and achieve faster processing speeds. Out-of-order execution rearranges the sequence of instructions to reduce delays caused by data dependencies. In scenarios involving a single instruction stream and multiple data streams, processors can optimize performance by disabling pipeline parts to skip redundant fetch and decode phases, particularly beneficial for repetitive tasks like video editing and photo processing. The evolution of CPU design has shifted towards multi-core processors and chip-level multiprocessing to enhance overall performance. By executing multiple threads in parallel, these approaches leverage task-level parallelism to boost efficiency. Multithreading allows CPUs to share execution units and memory system resources among multiple threads, optimizing performance while reducing the replication of components required in traditional multiprocessing setups. More recent CPU designs focus on achieving higher throughput by prioritizing the aggregate performance of multiple programs over single-thread performance, leading to the development of multi-core processors and chip-level multiprocessing architectures. Hardware performance counters have also become standard in modern CPUs, enabling low-level collection and analysis of software metrics for benchmarking, debugging, and security purposes. Modern CPUs feature privileged modes to support operating systems and virtualization. Virtualization in cloud computing allows the provision of a virtual central processing unit, vCPU, to individual users, distinct from a virtual private server, VPS. A host functions as the virtual counterpart of a physical machine, enabling the operation of a virtual system. Clusters are formed when multiple physical machines operate collectively, consolidating computing and memory resources. Some systems permit the dynamic addition and removal of resources within a cluster, which can be further partitioned into resource pools at host and cluster levels with fine granularity. The performance of a processor is influenced by factors like clock rate, measured in Hertz multiples, and instructions per clock, IPC, determining the instructions per second, IPS, the CPU can execute. Realistic workloads vary in instruction complexity, unlike artificial sequences with few branches, often used for peak IPS calculations. The memory hierarchy also plays a significant role in processor performance, often overlooked in IPS evaluations. To assess effective performance, standardized benchmarks like SpecInt are employed. Multi-core processors enhance processing power by integrating multiple cores within a single circuit, with dual-core theoretically offering twice the power of a single core. However, practical performance gains are around 50% due to software inefficiencies. Additional cores handle increased workloads, allowing for simultaneous task execution and handling of various events and interrupts efficiently. Cores within a processor can be likened to different floors in a processing plant, each managing distinct tasks. While multi-core CPUs boost a computer's multitasking ability, speed increments with added cores are not directly proportional due to intercore communication overhead. Specialized features in modern CPUs, like simultaneous multi-threading and uncore functions, optimize resource sharing for enhanced performance. Monitoring hardware use and performance levels has become intricate, leading to the development of hardware logic that tracks CPU resource utilization. Technologies like Intel's Performance Counter Monitor offer accessible counters to monitor CPU performance effectively.